Have you ever stopped to wonder what the secret sauce is behind a powerful medicine? It's not magic, it's chemistry. It's all about the incredibly precise arrangement of atoms that can fight a disease or even regulate our own bodies. Today, we're going to unlock a really key piece of that puzzle, a family of molecules known as alkyl halides.
So, take a look at this. This isn't just some abstract diagram. This is a weapon. This is chloroquine. For decades, it's been one of our most crucial defenses against malaria, a disease that affects hundreds of millions of people. And its power? It comes right from that specific chemical structure.
And it doesn't stop there. Here's another one for you, chloramphenicol. This little molecule is a seriously potent antibiotic, a go-to tool for treating nasty bacterial infections like typhoid fever. And again, it's that specific architecture that gives it its life-saving punch.
But what's really wild is that these compounds aren't just found in a pharmacy. They're inside us, right now. This is thyroxine. It's an essential hormone that your thyroid gland produces to keep your metabolism running. And you see those I atoms on the diagram? That's iodine, a type of halogen. They're absolutely critical for it to do its job.
So what do all these very different molecules have in common? Well, they all belong to that class of compounds called alkyl halides. In this explainer, we'll start by digging into their family tree, then we'll look at the chemist's recipe for making them, and finally, we'll see how you can control their reactions with incredible precision. All right, first up, the halide family tree. Let's map out the blueprint for these amazing and diverse molecules. So the official name for our stars today is alkyl halides, or you might hear them called haloalkanes. The concept behind them is actually wonderfully simple. You start with a basic hydrocarbon skeleton, an alkane, and you just swap one or more of its hydrogen atoms for a halogen. Fluorine, chlorine, bromine, or iodine. That one simple swap opens up an entire universe of chemical possibilities.
Now, to make sense of this huge universe, chemists use a kind of family tree. The very first major split in the tree is based on the type of carbon bond the halogen is attached to. Is it an sp3 bond, which is a single bond, or an sp2 bond, which is part of a double bond? Just knowing that one detail tells a chemist a whole lot about how that molecule is going to behave.
But hey, there's more than one way to organize this family. On the left, you've got that classification by carbon bond type we just talked about. But on the right is an even simpler approach. You just count the halogens. If it has one halogen, it's a monohalogen. Two, it's a dihalogen. You get the idea. It's a really flexible system for a super diverse class of molecules. So we know what they are, we know how they're organized. Now let's head into the lab. Next section, the chemist's recipe, where we'll see how these molecules are actually brought to life. Okay, so one of the most common and reliable ways to do this starts with an ingredient that's pretty familiar and easy to get, an alcohol. The basic game plan is to perform what's called a substitution reaction. You want to convince that hydroxyl group, that's the OH part, to leave and then replace it with a halogen atom, like chlorine.
Sounds pretty straightforward, right?
Well, there's a bit of a chemical catch. That OH group is actually very stable.
It forms a really strong bond, and it has absolutely no natural desire to just pack up and leave the molecule. So how on earth do chemists convince it to go?
In the language of chemistry, the hydroxyl group is what we call a poor leaving group. It's just not energetically favorable for that strong carbon-oxygen bond to break all by itself. It needs a little push, an external nudge. It needs a catalyst to kind of help it pack its bags and get it out the door. And that chemical persuader has a name. This little bit of teacher's insight from our source material just says it perfectly. The entire purpose of the Lucas reagent is to convert the poor leaving group, OH, into a good one. That's all it does. It basically tags the OH group, makes it unstable, and suddenly very eager to detach, which clears the way for the halogen to swoop in and take its place.
Next up, controlling the reaction. So we've got our recipe, we've got our catalyst, but now we get to the really elegant part, making a molecule with absolute pinpoint precision.
It turns out this reaction can happen in two totally different ways, and it all depends on the alcohol's structure. For the simpler, less crowded alcohols, it follows path A, an SN2 reaction. Think of this as a single, swift, one-and-done step. But for the more complex, crowded alcohols, it follows path B, an SN1 reaction, which happens in two distinct steps. Now, why does the path matter so much? Oh, it's a huge deal, because it determines the exact 3D shape of your final product. The SN2 pathway gives you what's called a 100% inversion of configuration. The molecule literally flips inside out. The SN1 pathway, though, that results in racemization, basically a 50-50 mix of both configurations. If you can control the path, you control the product shape. It's that simple.
And to really wrap your head around that SN2 flip, the source material gives us this fantastic analogy. Imagine the halogen attacking the carbon atom, but from the backside. The force of this attack literally causes all the other groups to flip over to the other side, just like an umbrella turning inside out in a really strong gust of wind. It's the perfect mental image for this complex molecular dance.
And look, this isn't just theory. This is stuff you can actually see in the lab. A chemist would notice the immediate evolution of these steamy white fumes. They'd watch the solid reaction just disappear into the liquid. They could even feel the flask get warm as the reaction starts releasing energy. It's chemistry in action.
And this is where that fundamental knowledge becomes a super practical tool. Those observable signs, especially those white fumes of HCl gas, are used as a simple and really effective test in the lab. If you add the reagent to some unknown substance and you see those fumes bubble up, that's a really strong sign you're working with an alcohol. So there you have it. We've gone from world-changing medicines to the hormones running through our own bodies, all the way down to the elegant dance of atoms inside a flask. And it all comes back to these alkyl halides, which just goes to show how much is possible with one simple chemical swap. The only question left is, what other secrets are still hiding inside these essential bonds?